Hello, guys. Only 3 today? 4? Well, I guess we'll do it anyway.
Bitcoin.
Hey, how's it going, guys?
It's still going alright.
You know, that's pretty much everyone's answer is as good as can be expected. So,
Let me just fix my camera. I mean, I don't have the coronavirus, so I guess I'm doing good.
or you're asymptomatic and you're just spreading it to other people. Yay!
No, I should be fine. I mean, I do have headaches, like, really often, but my parents are good, so, like...
Okay, that's what we all want to hear.
What about you, Miss Yokoi? You don't have nothing? You're fine?
Nope. Doing good. Been avoiding people pretty well. So, I only go to the grocery store maybe once a week maximum. And otherwise, I'm just here.
Do you find toilet paper?
No.
Do you find water?
No, but I don't buy water. Well, I find canned water. But
I mean, like, people doesn't realize, but you can just drink the water from tap water. It's pretty healthy.
yeah. And I have a filter. Plus, I do have an earthquake emergency kit. So I, by default, have a lot of water stored.
So what are we learning today, Miss Yokoi?
So today, I was going to kind of burn some time and see if anyone else shows up. But I guess this is the class today, all 6 of you.
It's been 2 minutes, Miss Yokoi.
Yeah, we'll see. Anyway, for today, one, I want to do the daily quiz, so I just want to check our VIR charts. I just kind of want to go over what's going to be the deal for this week. Also, someone want to call Giuseppe. I bet she's just still sleeping.
Aisling?
I called her already. She didn't pick up.
Okay, she's probably still sleeping. Anyway, and then as far as what's going on with the circuits lab, frequently tested, and what's going on with the practice test. I'm still new to the format of using the College Board classroom, so we'll, I'm sure, be working through issues on Wednesday. I'm not sure how we're going to do test corrections for that, but we're going to do them in some manner or form. Oh, a couple more people. All right, so first off, get yourself a piece of paper, a whiteboard, what have you, and work on the daily quiz. So for the daily quiz, we have a simple, it's technically complex because there's series and parallel, but we have a circuit that has a 9-volt battery, 3 resistors, A, B, and C. That's 3 ohms, 6 ohms, and 7 ohm resistors. And so I want you to do a complete VIRP chart for it. So how long do you guys think you need for this?
3-4 minutes.
Okay.
Yeah, around 3 minutes.
All right, so go ahead and work through this. I'll be back in about 3 or so minutes. I'm going to pause the recording so that it doesn't just have empty time on YouTube. All right, so to go over it, we have our resistors, the 3 ohm, the 6 ohm, the 7 ohm. We know our total voltage is
9.
9.
And what did we get for our total resistance?
9.
All right, do we want to go over how we got 9, or are we okay with knowing that it's 9?
I'm good. I'm good.
Okay, so from here, we know that our total current is just
1 amp.
1 amp, because V equals IR. And so now we want to figure out which of these can we transfer to somewhere else.
C?
Directly, yeah, C. What do we know about C?
The current is going to be the same as the total current.
Which means the voltage has to be,
7.
all right? What next?
A and B would have 2 voltage.
And then, what do we do?
And then we
Solve
divide
for
the
I.
voltage.
Divide the voltage by the resistance to get the current.
And does it, why is this one twice as high of a current?
Because it's the one that it goes through first.
It has less resistance.
Less resistance. So remember, it's not the order that matters, but how easy is it for the electron to get through? The easier it is, the more likely the electron's like, oh yeah, I'm gonna go that way. Since it is, this one is twice as difficult, twice as many are gonna go down the easier path.
Mhm.
All right, and then power is just multiply your V times R. And then what's our units for power?
Watts.
And then fact check, does all of our powers add up to our total power? We have 2/3 plus 4/3 gets us 6/3. 6/3 is
2.
2 plus 7 gets us
9.
9. So we must have done something right. Perfect. Are there any questions about
Wait.
this?
Power's. What is power? Resistance over.
There's a couple formulas for it, but your main equation for power is just V times I.
Okay.
And the reason for that is power is the change in energy over time, or the work over time. And since voltage is change in energy per charge, so that's how much charge or how much energy each charge loses. Current is how many charges per time. If I multiply those, my charge cancels out and I get change in energy over time again.
Oh. Okay.
That's how we got that equation. All right. Great question. Any other questions? Okay. So then I'm just gonna go over like what's the deal for this week. Theoretically, you guys are turning in homework 12 today. Many of you already have, so just do that when you have a chance. I'm gonna be posting problem set 12 again. Problem set 12 is probably just going to be, I haven't entirely decided exactly which questions, but it's probably just going to be review questions. So I'm gonna just start pulling old things together so we have a chance to talk about them, gives you a chance to rethink about them. Videos. So videos for this week are going to be a review. I'm going to assign flipping physics videos, but I'm probably also going to especially assign some of the AP sponsored review videos because most of them are on rotation, and I know rotation tends to be one of our weak spots. And then at the end of this week, I think on Friday, they're doing one on forces and equilibrium, which is also one of our weak spots. So I'm going to be probably assigning those at some point, maybe this week, maybe next week, depending. Either way, I would take the chance to go watch them. They're better live because you can kind of get responses in real time, and you can actually post on Twitter to at least Jacob's Physics on his days and get responses to questions. And those, unfortunately, are 9 a.m. our time, 12 East Coast time, because they're both on the East Coast. All right, as far as your circuits labs, today, 7 is due today. Is that going to be a trouble for anyone? Do we need to push it?
Is it complicated?
Not any more complicated than the other ones.
Okay.
And then as far as the circuits labs, there are 8 and 9. I would do them, but 8 and 9 are actually extra credit. So I'll post an opening for them, but they are technically ungraded assignments and will go in as such because they're extra credit. So they are your extra credit opportunities for this time period.
Mr. Coy,
Yes.
can we push the circuits lab one day back?
Yeah, I can. Or if you, I'll probably still push them today, but if you turn them in late, it's not going to be a penalty.
Okay. All right. Thank you.
I'm pretty much not penalizing any late work because this is a weird time for everyone. Everyone has different things they got going on at home. If you just aren't doing anything, that's going to catch up to you. But as long as you're like working towards it, it's not going to be a penalty. I just want us to have a chance to review and actually learn things during this odd time in our lives.
Mr. Corey,
Yes.
about the circuits lab,
Mhm.
I've been looking for them, but I think I just didn't grab a third resistor, like different from the other ones.
Got it. If you still have my number, text me on Remind, and we can arrange like a pickup date for resistors.
Okay, I'm not sure because I'm not sure how like my parents would be about people bringing stuff here because they've been very cautious about everything.
Yeah. So what I can do, I can put them in a disinfected bag and leave them like out on my doorstep if you don't want to like interact with anyone, or drop them on your doorstep, whichever you prefer.
I feel like that
Mhm.
I'll talk to it with my mom.
Yeah, figure out what works for you guys.
Mhm.
Let me know. Worst case scenario, we can do other things. Yes, Eduardo, still raising your hand?
Oh, is it normal? Like the battery I have doesn't have all the volts.
No, not anymore. It doesn't.
No.
The longer you leave it attached, the more voltage you'll notice as these go on, the less energy it's gonna have because it uses your battery's dying. That's not.
So instead of having 9, can I keep using it as 8 something?
Yeah, it's normally when it gets down to 7 or 6 when it's probably just done. But if you're still in like the 8 range, you're probably still fine. If it drops down to 5, it's dead. You can still use it, but you're just going to be getting some very odd voltages off of it, and that's okay.
Wait, so quick question.
Yeah.
So regarding like April, are we just gonna be doing reviews?
Yes.
Or so like April strictly review.
Yes.
Okay. All right. Thank you.
Speaking of that, either today or tomorrow, because I don't want to post too much. Well, I guess it's online. You guys can look at it whenever you want. But I'm going to be posting. I think I took pretty good PDF pictures of them. Let me know if anything's unviewable. But I'm going to be posting. I have a list of frequently tested but difficult questions, along with an answer key. And so basically the goal is, yes, could you cheat on this assignment? Absolutely. But the goal is that it gives you practice with immediate feedback if you want it, and then you're welcome to ask me any questions about it on Friday. Friday is probably not going to be new stuff. Friday is going to be more like office hours and review of things we've gone over this week. Kahoot, Eduardo put together Kahoot. Have you done the second one yet?
No.
Okay. So when Eduardo puts together the second semester Kahoot, we'll probably do like a Kahoot session to be determined. And that'll essentially count as our test. I'll make a special announcement and maybe at a special time just so we can make sure everyone can get on.
Wait, have you tried it?
I haven't gone through it yet. I'll obviously do testing before we push it to everyone.
Okay.
But thank you for doing the grunt work.
And then the answer for the second semester is on YouTube, right?
Yes. And so if you haven't yet seen it, I did post all of the answers to the flashcards on YouTube. If you really want, I can go over it, but I think I did a decent job. The only one I think I didn't do a good job is resistivity. That's because you're doing a resistivity lab, so I didn't want to like completely spoil everything. As far as what we're doing today, we're going to be working on light bulbs and brightness. Again, not this year, but most years, light bulb brightness questions are very common. And that's in page 8 in your packet. And then I'm going to also be posting Pivot Interactive's Resistivity Lab. And then the practice test is going to be on Wednesday. So on Wednesday, like plan on having time to take the practice test. It's going to be multiple choice and FRQ. I think I'm going to use 2017. 2018, I think 2017 was a better year in my opinion. So it's going to be a practice test. Take it all the way through, treat it like an actual test, and then we'll just see how you guys did and do test corrections and answer questions on the things like that. And then hopefully that can help me identify how to focus the review going into April. Any questions about what's going on this week? All right, so I'm going to erase this. Please take out your big packet. Turn to page, which looks like this. And Navi, I think bunnies are a pretty good first pet. They do live longer than rats, so just, you know, if you're planning on going away to college, keep that in mind if you plan on getting pets at this time.
Wait, you can get pets in college?
Not in the dorm room, which is why, I mean, if you're renting your own apartment, it depends on the apartment.
Oh, okay, but I mean like inside the college.
Wait, what'd you say about bunnies?
I do like bunnies. I find rats to be smarter, which I value relatively highly in my pets. But, well, that being said, I have pretty dumb dogs, but my rat is probably smarter than my dogs. But I do really like bunnies. They are definitely trainable. You definitely want to litter train it. And then just be careful where you get it from. Turtles are cool. They're like most reptiles. The less you interact with them and clean their environment, probably the happier they'll be. Turtles, most reptiles don't really want to interact with you. You're just sort of like a food source, and that's cool, but they're not really in it for the attachment, and some people really like them. All right. So this is page 8 again.
The famous Russian husband,
What?
the famous husband.
Uh-huh.
When is he gonna tell us hi, music?
When he feels like it. It's a free country, sort of, right now. Okay. So, puzzle 1 says we have a battery and we have 3 light bulbs in this. So what's going to happen to the brightness of each light bulb when I close the switch? So I'm going to number them here. All right. Does anyone have any predictions? So first of all, what is brightness, or what controls the brightness?
Is it the voltage, the power?
Power.
Voltage, power.
So that means it depends on voltage and current. So that's why they like to ask these questions, because it forces you to think of both the voltage and the current at the same time. So what we're really thinking, or anytime you see brightness, you want to think power. Which one is more important, voltage or current?
Voltage?
Would they be the same?
Yeah, it was a trick question. Sorry about that. They're going to be the same, right? There's no square in here, like it's basically, it's like momentum. Mass and velocity are equally important. Voltage and current are equally important to the power. So we want to think, what's really going to change when I close this switch? What's going to change for our circuit?
It's gonna be closed.
It is going to be closed. What's going to happen when it gets closed?
It's
Wouldn't
gonna
it go-
become dimmer.
Only through 2? No, it will make it brighter, wouldn't it?
So,
It'll make them dimmer.
well, it depends on which one you're talking about.
Wait, you say closed or open?
closed. So let's say I close this. Well, let's say it's open for now. So it's open. Which way does my electron travel?
Two.
1 and 2.
1 and 2. So right now with the switch open, it only hits 1 and 2. So is this a series or a parallel circuit right now?
It's in series.
Series.
Series. And so they're get the same current. They're the same light bulb, which means they have the same resistance. Notice when they say, normally when they refer to light bulbs, they normally specify. But if they don't specify, it's assumed that they're all the same light bulb, which means if it's all the same light bulb, they have the same resistance.
Yeah.
What was that?
So when right now, what do I know about the brightness of 1 and 2?
1 is brighter.
Do they have the same resistance?
Wait.
Yes.
Yeah.
Yes.
Have the
Oh, what
same,
if they have the same thing? Never mind.
so 1 and 2, right now, 1 and 2 are equal. Is that true when I close the switch?
No.
Probably not, because what have I done?
You divided the.
You've added another component.
I added another path. So did my overall current increase or decrease when I added a new path?
Decrease.
Decrease.
My total
Wait,
current.
no.
Wait. When did you do this?
Doesn't it stay the same?
Well, let's think about this. What
It
did
increases.
what did I change?
You added more paths. So
I
like
added more paths. So did I increase the resistance or decrease the resistance?
Increase.
increase, right? No? Because you have a light bulb.
Yes. So this is the interesting thing. That's
Oh,
confused. Anytime you add something in parallel, your resistance is going to decrease. Always. And so we can assign them some value if you like, but basically, let's say if this is R, this is R. Originally, my resistance was just 2R because there was 2 of them. Now that this is in parallel, I have to do 1 over R plus 1 over R. And then flip it, plus R. So instead of 2R, I now have 1.5 R. So this was my original resistance, just these two. When I added something in parallel, I decreased the resistance just by a little bit. Since the voltage of the battery stays the same and my resistance decreased, my total current increased. So if my total current increased, which one benefits the most from a total current increase? Or which one gets the total current?
The series.
The one in series. So number 1 is going to get more current because of this. If number 1 gets more current, but has the same resistance as everyone else as it had before, what's going to happen to its voltage?
Wait, what, can you repeat that?
Yeah. So yeah, light bulb questions, if you're like, oh, this looks simple, light bulb questions are common because they're considered difficult. And so if you encounter a light bulb question and you don't know how to do it, one thing that you can do if you have the time, you can do a VIR chart or a VIRP chart and then just make up a random number for their resistance or voltage. And then do what changes. So if you have trouble conceptualizing it, you can just brute force and do the math the whole way through. But basically, we have added another path. And to look at it even better is we can see that there's still only one path through 2 and only one path through 3, but now number 1 has 2 paths through it. It's going to get more current. And if it gets more current and my resistance hasn't changed because it's the same light bulb, it's also going to get more voltage. if I increase my voltage and my current, what's going to happen to my power?
It's gonna increase.
Going to increase. So the brightness for 1 is going to increase brightness. So, and remember, the amount of voltage this battery gives out is finite, which means if that was a 9-volt battery and number 1 is taking more voltage, what does that mean for number 2?
It gets less.
It's going to get less voltage. Also, I have a bit more current, but I probably didn't double the current because I didn't have the resistance. So if I now have a current split, is number 2 going to be getting more current than it did before or less current than it did before?
Would it get more because the parallel is
So-
getting less?
It depends. But in this case, ooh, you guys can really tell the cloud just went over. At least I can here. But so for number 2 is going to get less current. Because before, even though it wasn't as much current, it got all the current. One thing for sure, the current definitely didn't increase because now they have a choice. And we could, and if you want to, we can. I can solve all of this out with variables and show you exactly how it's changed. Would you guys like me to do that after we go over this?
Yeah.
Yeah.
So I'll go do that after. I'll solve it. We'll do it conceptually first and then mathematically. And so 2, brightness has decreased because it's getting less current and less voltage. Same resistance. 3, by default of the fact that it wasn't lit at all, 3 technically has increased brightness because it wasn't even lit in the first place. But your order would be, if I was to say list them from least bright to most bright, or excuse me, most bright to least bright, it would be 1 is brighter than 2 is equal to 3. And so that would be the order of the brightness. 1, and this is what hopefully you guys found when you played with the light bulbs a little bit last week. 1 is looking brighter because even though it's in series, or because it's in series, it gets the whole current. And because it gets more current and it's the same resistance of the other 2, it's going to also get more voltage. These sort of conceptual rules only really work when you all have the same resistance. Otherwise, you do have to calculate it out. And so on that note, are we okay with me erasing this? I'll go through and do the entire mathematical version of this.
Yeah, that's fine.
Yes.
Okay.
Are try not to move your shoulder? Are you trying to not to move your shoulder?
Yeah, it's better, but I just don't want to lift my left hand above my shoulder. Okay, so do you want me to do 1? I'll just do 1 with only 1 and 2 before the switch is closed. And then okay. So in the beginning, we just have 1 and 2. Let's just say there's some resistance R. So their resistance is just R. We have some initial voltage B. Our total resistance, because they're in series, is just 2R, because you just add them together. And then that would mean our current is the voltage over the resistance. And since they're all in series, their current is all the same. And because of this, they each are in series. They have the same resistance. If I multiply these together, they each get half the voltage. Which means their power, this is about to get a little ugly. Their power is going to be V squared over 4 times R. Just because that's V times I. So later, they also have some resistance R. However, and they still have some total voltage V. My total resistance is not going to be 2R. I'm going to have to add these in parallel first. 1 over R plus 1 over R, which gives me 2 over R. Which means my resistance for the parallel is just half of R. Plus the original R gives me 1.5 R, or 1.5 R. I'm going to leave them as fractions here. And so I'm going to make this 3/2 R. And so that makes our current now 2/3 V over R. So V divided by so, and we can see right now that this current 2/3 is bigger than 1/2. So my current, like we predicted, my current did increase. And so number 1 benefits from this current increase. Because of this current increase, it will also benefit from a voltage increase. All right, because if you push more electrons through there, it's going to get more voltage as well. So if we multiply this out, we'll just get 2/3 V, an increase from 1/2 of V. And then these ones only get what's left over. We have a total of V, so these get 1/3 V. And they will equally split this they'll equally split this current because they're equal resistance, 2 parallel paths. So they also get 1/3 V over R, 1/3 V over R. And so if we solve for power here, we're going to get 4 over 9 V squared over R. Sorry, I just want to write this a little neater. So it's 1/4 V squared. Wait, because I did my notation bad. There we go.
Mr. Coy,
Yes,
how'd you get power again?
voltage times the current. So I get 1/3 V times 1/3 V over R, which so I have 2 V's, V squared, still divided by R. And then 1/3 times 1/3 gives me 1/9. And that's true for both of these. This one is 2/3 times 2/3, so I get 4/9. And so this actually kind of opens up an additional power equation. Power is also V squared over R. And all it is we solve for I, and then instead of using I, we plug in V and R for it. And so there's multiple equations for power just by using P equals I times V, and then you use Ohm's law to plug in whichever one you are missing.
Oh,
Sorry about that, Jan and Jean. And so this one we still get oh no, we don't. And so we get 2/3. So we get v times I here, so that'll give us 2/3 v squared over r. And so, and that's why, because some people were like, well, it's the same voltage, shouldn't our power output remain the same? No. Or shouldn't our total brightness be the same? Because when you open up parallel lines, you decrease the current. And because you decrease the current, or excuse me, you decrease the resistance, increase the current. If you increase the current, you have more electrons flowing. The more electrons you have flowing, the more power they use, because the more energy they use. And so we can see that the total power of my new circuit with the switch closed uses more power than my original, which is why this one can be so much brighter. Because this was 1/4, and now this is almost 1/2. So it's almost uses as much, this one now uses almost as much power as this whole circuit did originally. So, which is why putting things in parallel makes things brighter, but it also uses a lot more power because of that, right? If it's brighter, it uses more power, you're using more power, you're using more energy. And so this is how you can, and then if you don't like variables, but you don't know how to do this conceptually, you can just make up a random R value, make up a random V value, and solve it like you would any other problem, and then compare your powers. For me, I like doing it conceptually because I find it faster, but if you need to do it mathematically, you can absolutely do it mathematically. Any questions about this, or do we want to try a new one?
Mr. Coy, for the current in the second chart, it's not the same, right?
No. So, yeah, so that's a good to point out. So so between this to this chart, our currents increased, our voltage stayed the same, and our resistance decreased. So when you add something in parallel, your overall resistance decreases, and if that decreases, your current increases because you aren't actually changing your battery. You are using it up faster because our power increased. And so this is why I said when you are doing your circuits labs, especially when they're in parallel, if you leave them in the parallel one, you will burn out your battery much faster. Because yeah, your battery still provides the same voltage, but you're draining power a lot quicker. You're using a lot more power per time, or a lot more energy per time.
Okay.
Great question. Any additional questions? Those I threw a lot of math at you kind of quick.
Mr. Coy, for the voltage, you got, for the second chart, you got 2/3, 1/3, and 1/3?
For the voltage?
Yeah, for 1, 2, and 3.
Yeah, 2/3, 1/3, 1/3.
And that ups to 1, sorry.
Yeah, because it's, remember, each path. So we have 2/3 plus 1/3 gets me 1. And then 2/3 plus 1/3 gets me 1.
Mm-hmm.
This is the parallel. You would add 1 and 2 to get your total voltage, and then 1 and 3 to get your total voltage. Since these are since 4, 3 existed, 1 and 2 were in series, so you would just straight up add the voltage.
Oh, okay, I see.
And then for this one, your current should be equal to the total current, and these two currents should add up to the total current.
Oh, okay. Yeah.
Good question. All right. Any additional ones? And I think number 2 is kind of hard. I may put on like a slightly easier one before that. Any questions?
I think that's it.
right, so I'm gonna make up one because number 2 kind of ups the difficulty rather quickly, I think. So I'm gonna make up an easier one. I'm gonna erase all this. Um, Okay, so we have resistors A, B, and C all in parallel. No series, just parallel. And C's switch is disconnected. When I close the switch, what's going to happen to the brightness of A, B, and C? Right. So what things do we want to consider?
It will get brighter or it will stay the same.
Okay, so either brighter or stay the same. All right, why?
Because I remember like how you said the resistance is gonna go down,
Okay.
and then the voltage will increase. Or no, the voltage will stay the same. The current will increase.
So the total current will increase.
Yeah.
What's going to happen to the current of each individual?
It'll stay the same.
Okay. Why?
Because you're just adding another path. You're not doing anything to the existing path.
Okay. Any other answers? Do we want to do the math?
Yeah.
I mean, it's not like you really want to, but like, sure.
So actually, Navi is exactly right. I'm not sure for the right reasons yet, but here's what happens is yes, the total current absolutely increases because the total current decreases. However, the amount that the current increases pretty much just gets siphoned off into C. So nothing actually changes for A and B. And so we can prove this again. I shouldn't have erased these. So
Mr.
yes,
Did you make this one up?
yep.
Oh,
That's why it's number square root of 2, 1.44.
okay.
Okay, so since they're all in parallel, they all have
Whoa.
the exact same voltage as the battery. So we're like, okay, that part's easy. They all are the same resistors. The difference comes with the total resistance, total current. So this one, we're going to add 2 resistors as a fraction. And for this one, we're going to add 3 resistors as a fraction. So this one, so the resistance is greater if there's only 2 in parallel. The resistance is lower if there's 3 in parallel, because there are more paths. And so because of this, the current is going to be greater during the time where there are more paths. So it's going to be V divided by R equals I. So this one's going to be 3V divided by R. This one's going to be 2V divided by R. And so basically, because they're equal, they're going to split. Remember, in parallel, they split the current, keep the same voltage. So the parallels are going to, they have the same resistance, so they're actually going to split the current equally because there's no path that's easier. So really, your electrons are just going to go, they're going to spread equally because they're like, it's all going to be trafficy. We're just going to pick whichever one less carded went down last time. So they're all just going to be V over R. And that's true here as well. Because basically this 1 over R of current that we added is just the current that C needs.
So they're basically adding up.
Yep, so they end up actually being, nothing changes for A and B. The only thing happens is C turns on. Again, this is also why your house is wired in parallel. They don't wire it in series, because if they wired in series, your bulbs may literally change brightness. So again, if you turn on lights in one part of the house and the lights in the other part of the house get dimmer, you should fix your electrical. Something's wrong. It shouldn't do that. And so that's pretty much why, because every time I open it up, I decrease the resistance enough so that I get current to my new part. And that's, again, how your house works. Questions about this? I'm going to take that as an okay. Do we feel ready to try number 2?
Yes.
Yeah.
So number 2 doesn't have any switches. The number
I have
2 is ranking the brightness.
So we just have to rank it. That's
Can I
it.
put what I think,
Yeah?
or can I say it? My bad.
Give people a chance to think, and then absolutely I want to hear it.
Okay.
All right, so we have our light bulbs here. Before we even make predictions just yet, what's the arrangement? What things are in parallel? What things are in series?
1 and 2 are in parallel.
All right, 1 and 2 are in parallel.
3 and 4 are in series.
3 and 4 are in
And
series.
then 5 is in parallel with 3 and in parallel with 4.
So we have 2 kind of separate parallel sets. What we have 1 and 2, and 3, 4, 5. So, Cindy, you want to make a prediction?
Basically, what I think is like the second block is going to be brighter than the first block.
So,
Like 3, 4, 5 is equals to each other. And then greater than 1 and 2. And 1 is equal to 2.
oh, okay, I see what you mean. Okay. All right, do we have any other predictions?
Well,
I think they're 1, 2, and 5 will be the same. And then they'll be brighter than 3 and 4.
Okay.
I say 1 and 2 are the same, but they're like higher than 5, greater than 5. And then 5 is greater than 3 equals 4.
So I'm definitely seeing some trends here. So we seem to think there's a connection between 1 and 2, 3 and 4, and then maybe 5 somewhere in there. Why do we think 1 and 2? Because everyone said 1 and 2 are the same and 3 and 4 are the same. Why do we say that?
Because they're in
They're parallel.
parallel.
Okay, so if they're in parallel, what do we know about them?
They have the same power
Same brightness.
All right, why?
because they have the same current and resistance.
So
Wait, Mr. Coy,
yes.
but wouldn't 3 plus 4 equals the same as 5? Like, if you,
We'll get to that in a second. I think I know what you're getting at, but let's focus on this part first. So yeah, 1 and 2 are the same because they get this, they have the same resistance, they get the same voltage because they're in parallel, therefore they're gonna get the same current, and if they have those the same, they're gonna have the same power. And then sometimes it may be easier to use the other definition of power here because we know they have the same resistance. So really all we care about is who has more voltage. All right, so we're definitely sure that 1 and 2 are the same. All right, why did we put 3 and 4 the same? They're not in parallel. Well, we don't know why we put them as the same, do we?
they're in
They're in
series.
parallel to 5. Like,
Question.
Well, 3 and 4 are in series. What does that tell us?
They have the same current.
same current.
Same current, and they're the same light bulb, so they have the same
Well,
resistance,
resistance.
which gives us, I actually have to plug this in.
But how does that connect to 5?
We will get there. Sorry, I'm just gonna write all the definitions of power. So basically, I still use this one because this is the main one, but when I'm doing power and I know that the resistors are the same, I like to use this one, which just comes from plugging in V equals IR into the original equation for either V or I. And so basically this tells us that they either need to have more voltage or they need to have more current depending on the resistance. And for here, since they have the same current, same power, they have the same resistance, same voltage, same resistance, same power. All right, and so what does this have to do with 5? Well, if you were an electron and you had a choice, right, because how many paths do I have here? How many different paths do I have? There are 4. There are 4 different paths. I could do 1, 3, 4, home, 1, 5, home, 2, 3, 4, home, 2, 5, home. So if you were an electron, 1 and 2, it doesn't matter. They're the same. Would you choose to go down 3, 4, or 5?
5.
Why?
5.
Less traffic.
Yes, I
Yeah,
was gonna
less
say that.
resistance.
traffic. So less traffic, less resistance, therefore more current. So I know that if I'm an electron, more electrons are going to go down path number 5 instead of 3, 4 because there's less resistance. If
I'm gonna write that as my explanation on the AP test.
I
Less
mean,
traffic.
There's no
Does it
circuits
count
on
that
the
or
AP
no?
test.
just switch in the word resistance and you're fine. So more current, and who's going to get more voltage, 3, 4, or 5?
5.
No, 3,
Wait.
4.
Depends how you think about it. 3
5
plus 4 has to be equal
equals
to
5.
5, which is
Five.
sounds really bad.
That's five.
The voltage.
That's
from
what I said.
because remember they're in parallel. So 3 and 4, the total voltage on this side has to add to the total on this side. So that means the voltage of 5 has to be greater than the voltage of either 3 or 4. Therefore,
5 is
5
brighter.
is going
Yeah.
to be brighter than 3 and 4. So we know 3 is equal to 4, 1 is equal to 5 is bigger than 3 and 4. What about 5 compared to 1 and 2?
Oh. No, wait, never mind. I was gonna say no.
Well, if you think of the 1 to 5 and the 2 to 5 like that path like separately, wouldn't they be like series? And wouldn't that kind
Series.
of be like how 3 and 4 are?
Okay, so let's say we have some total voltage, and the full loop would be the voltage from 1 minus the voltage from 5 equals 0. The other loop through 5 would be the voltage from 2, the voltage from 5 equals 0. And so the question starts to become not the voltage, but V equals IR, right? So I'm going to replace these with IR. And I'm not going to do number 1 because it's exactly the same as number 2. Okay, so basically we're trying to figure out what's bigger, the current and resistance of 1 or the current and resistance of 5. What do we know about the resistance?
It's the
They're the
same.
same.
It's the same. Who gets more current, 1 or 5?
It's the same.
Is it 5 or the same?
I don't
The
know.
same.
5.
5 because it increases.
Yes. So I'm gonna get rid of the math because you can make up numbers and do the math for these. I really hate doing that. But it's like we said before, this gets more current. And so let's say we have some current. Do you want me to use the letter I, or would you like me to make up a number?
I like letters.
Use I.
Okay. So we have some total current I, which means 1 and 2 are the same resistance. They split it equally. So this gets half of I, and this gets half of I. However, here, we're going to split it unequally because this is twice as difficult to get through. So instead of half, this is going to get 2/3 of I, and this is going to get 1/3 of I. And so because of this, they all have the same resistance, but this is going to alter their voltage. Or we could even just use this equation. It's basically whoever has the most current, you're gonna have the most power for the same resistance. So basically, because this one has more electrons traveling through it at any given time, it's going to have more voltage, it's gonna have more energy, it's gonna have more power, it's going to be brighter. So the full order is 5, greater than 1, 2, greater than 3.
Wow. Holy cow.
So what I would like you to do right now, again, I can't force you because I can't see it, but try to write yourself a paragraph or like 3 sentences summarizing why this is the order. Just because probably in the process of writing it, you're going to come up across of like, wait, why was that actually true? And then we can answer those questions. So I'm going to pause the recording and give you guys like 5, what do you think, 3 minutes, 5 minutes?
5.
It is then. 4 minutes. Try to write yourself a paragraph and identify where are places you still don't understand so we can answer some questions. All right, see you in 4 minutes. So the question was, why are 3 and 4 the same? So 3 and 4 are the same because since they are in series, they share the same current. And since they share the same current and they have the same resistance, they will also have the same voltage. And if they have the same current, the same voltage, the same resistance, they will also have the same power, same brightness.
So if there were different resistors, they will be different, right?
Yes. If they were different resistors or say different light bulbs, so that's why if you're trying to like wire something and you're using two different types of light bulbs, lamps, especially lamps that have multiple, they're like, you have to use this type of light bulb, otherwise your brightness is going to be all over the place.
But in parallel, the resistance doesn't matter.
It does still matter in parallel. Because let's say, because since these have more resistance because there's two of them, that kicks more current over here. So if these did not have the same resistor, they would not split the current half and half.
But wouldn't they have the same voltage?
Yes, they would have the same voltage, but not the same current.
Okay.
And therefore not the same power. So basically, if your resistance changes, so does your power. If your voltage changes, so does your power. If your current changes, so does your power. All right. Any other questions you guys uncovered in your answering or your summarizing of this problem?
Can you explain how 5 has more of a current than 1 and 2 again?
Yeah. So I'm gonna. Should I make this neater? It's getting hard to read.
I can still read it.
Okay. I'm gonna get rid of some junk here. Okay. So because 1 and 2 are going to split my current equally, half and half. 3 and 4 and 5, however, right? Remember, going through here, we still have the same total current because we haven't lost any. Charge is conserved. I had total current. The moment my circuit comes back together, I have the total current again. But here, this junction has an unequal split. So because of this unequal split, more current is going to go down path 5 than path 3 and 4. And I know, because I've done this a lot mostly, but if this has half the resistance, because it's only one resistor, if this has half the resistance, it's going to have twice the current. So whatever this one is, this is going to have twice the current, and it's still going to add up to 1. So I know the only way that happens is if I do 2/3 and 1/3. So if this current is 1/3, it's half of my current over here, because it's twice the resistance. And total, my current still adds up to 1. And so since 2/3 of the current is greater than half of the current, 5 gets more current.
Mm-hmm.
Great question. I think that's normally the most complex part of this. Is figuring out 3 and 4 are the same, 1 and 2 are the same, but where 5 fits in, I think, is always the more difficult, most difficult to answer on these questions.
How's the voltage affected in that situation?
Okay, so voltage is affected based off of Ohm's law, V equals IR. So we don't really care about the resistance because it's the same. Nick, if you're watching this, that doesn't mean the number's not important, but it just means it's not going to change the ratio. Because here we don't care about the number, we just care about the ratio. So my resistance is all the same. If my current increases, my voltage doesn't equal measure because they are directly proportional.
Mm-hmm.
So 5 gets the benefit of both having the most current, and because it gets the most current per the same amount of resistance, it's going to get more voltage as well.
What about for 3 and 4?
Same thing, and actually even less so. So 5 is going to get more voltage because of this, but 3 and 4 have less current.
Mm-hmm.
And then 3 and 4 both have less current, and another way to look at it is the voltage from 3 plus the voltage from 4 has to be equal to the voltage from 5 because they're in parallel. So the amount of volts on this side has to be equal to the amount of volts on this side. So because they have half the current, they're each going to have half the voltage that number 5 has.
Okay. So then compared to 1 and 2, they would have like also less than that.
Yeah, they will also have less voltage because, again, same resistance, less current, they will get less volts.
Okay.
All right, we ready to try another one?
Yeah.
Yes.
Do you want to try number 3 or do you want me to make up one?
Number 3.
Oh, so let's do number 3.
Mr. Coy.
Mhm.
Josephi just woke up.
Oh, there she is. Okay, so the numbering is a little weird, which I've never actually noticed that, but basically same idea is what happens to the brightness of 1, 2, 3, and 5 when we close the switch. So something I would like you to do to start is rank your brightness with it open. And so what I want us to do is first rank it with it open. So like there is no 5 or 4, it's gone. And then try to rank it with it closed. All right, and so we're going to tackle with the switch open first. And so remember, open means it's not connected. There's no connection. It's the bridge is up. It's not working. So if it's open, what circuits or what things do we have to consider?
2 and 3 are in series,
2 and 3 are in series,
and then 1 is parallel with them.
and then 1 is parallel with them. And so if I had to rank 1, 2, and 3, what would be my ranking here for brightness? Which one's going to be the brightest?
1.
1
Okay, why?
because it's
Less resistance.
All right, so this one's, so the current through path A is going to be greater than the current through path B because of less resistance. All right, what else?
it doesn't have to split the voltage.
So yeah, so and it also gets more current and it gets the total voltage of the battery. Absolutely, it's going to be brighter. What about 2 and 3?
They're equal.
2 and 3 are going to be equal. All right, so do we feel comfortable with this ranking of brightness?
Yeah.
Okay, so to rehash, 1 is going to be the brightest because it gets the full voltage of the battery. It also has more current because 1 light bulb is going to have less resistance than 2 light bulbs, so it's going to have more current. And again, if you have both more current and more voltage, you're going to have more power. You're going to be brighter. What about with this closed? What changes if I now close my switch?
3 is now parallel to 4 and 5, and 4 and 5 are in series.
Yes. So 3, and so remember 5 is just the switch. I numbered it, but don't worry. Yeah. So now 3 and 4 are in parallel. All right. So what's going to change? So when I close this, what changes? Does
More
the voltage
current.
change? Okay, more current. Where do I get more current?
Between 5 and 4.
Okay, so we're gonna get more current here. Am I gonna get more total current? Is it stealing someone else's current?
It's gonna be spread out evenly or somewhat.
So did I, if by adding a parallel, did I increase the total current of the circuit?
No.
No.
Yes.
Just a little bit. So anytime you're adding parallel, you decrease the resistance at least a little bit, which means the current increases at least a little bit. All right. So I have increased the current here. So between here and here, does this area have more or less resistance?
Less.
Is less resistance, which means this path is going to get more current now. At least more so than it had before. All right, is it going to get more current? If I add this in parallel, does this line have more or less resistance than number 1 by itself? What do we think?
Wait, can you point out the line again?
So does this 2, 3, 4 block
Mm-hmm.
have more or less resistance than the 1 by itself?
More,
Yeah, it has
because
more.
it's more
It
bulbs
has
and
less
stuff.
than it had before, but still more than number 1. So number 1 is still going to get the most current and all the voltage. So which one's going to be the brightest?
1.
1 is still the brightest. 1 is still the brightest. All right, are 2 and 3 going to be equal anymore?
Yes.
Mm.
But less.
All right, yes, but less.
Wouldn't they get brighter, but like they're still the same?
So before 2 and 3 were the same because they got the same.
Current.
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 Do 2 and 3 get the same current anymore?
No.
Oh wait, no.
Who gets more current, 2 or 3?
2.
2. And so if 2 gets more current for the same resistance, it's also going to get more
Voltage.
voltage. Because this is going to be a constant because they're all the same light bulb, same resistance. So now 2 is going to be greater. What about 3 and 4?
3 is greater
Why?
because it's in parallel. Oh wait a minute. Wait, never mind.
They'd be the same because they're in parallel,
Yeah,
so they
it's the
get
same.
equal voltage. And they already have equal resistance.
They have equal resistance. They're in parallel. They get equal voltage, which means by default, they get equal current. And so your new order looks like this. Right. So some things to consider. Did 2 get brighter or dimmer?
It got brighter.
It got brighter compared to 3, but
And
it's still less than 1.
yes. And what happened to 3?
3 got dimmer.
All right. What happened to 4?
The same.
It just turned on.
It just
Well,
turned
it
on.
was
You know,
off.
it's
Yeah.
just happy to be here. What about what happened to 1's brightness though?
It got the most, but less. Or
Isn't it the same because it's like one big parallel? Like,
Yeah, I'm just doing some math to confirm. I'm pretty sure you're right, Cindy, but yeah. Basically, because we added this in parallel, we increased the total current, but the amount we increased the current was just enough to turn number 4 on, basically. And so number 1, it's nothing affected its line. It's still just like, did anything change? Something happened over there? So number 1 gets to stay as bright as it was. Number 2 gets the added bonus of that little bit of current, so it got brighter. Number 3 now has to share with a new sibling and got dimmer because of it. And 4 again, it's just happy to be here. Happy to be nominated. All right. Questions about this one?
Mr. Corey, Josephine has a question in the chat.
Oh, thank you. So the current in 1 and 2 are not going to be equal because it's not equal resistance. The total voltage in each line will be the same, but again, these are going to have to split their voltages up. Number 1 just gets to keep all of it. So if we say had 2 light bulbs in parallel, same resistance, same voltage, same current, because they're equal to each other, the same resistance. But your electron would rather go down the path of least resistance. So there are now more paths through 2 than there were before. But remember, if my electron chooses to go this way, it's still going to hit 2 bouts of traffic versus only 1. So more electrons would rather go down path with the 1 instead of path where no matter what happens, they're going to hit 2. Yes, it opens up into a 2-lane highway, so it works a little bit better, but it's still not just 1 toll booth. We still have 2 stops here. Good question. Hopefully that answered it. Great. Any other questions?
So, Mr. Corey, for the reason that we said 1 stays the same is because 4 had to be turned on with the current that was added.
Yeah, so basically when you add things in parallel, and it does seem counterintuitive, I agree, but when you do the math, if you want, we can do the math. When you add another line, basically that added current was just the amount of current needed to turn this on again. And so basically the loop for number 1 has not changed because that the blue line, that's our added current, and that now added current goes to number 2, but it doesn't actually affect number 1.
Oh. Yeah. Thank you.
No problem. You ready to do number 4?
Yeah.
All right.
Yes.
Let's go ahead and take a look at number 4. I'm going to erase and draw. All right, so what do we think? I mean, let's point out which things are going to be equal, because I think we're pretty good at identifying those.
1 and 2 and 4, 5.
In no particular order, but just 1 is equal to 2, 4 is 5. Why is 1 equal to 2?
Because they have the same current.
Why?
Because they're in series.
All right, they have the same current in series, and
They have the same resistance.
therefore the same power. All right, why are 4 and 5 equal?
They're parallel to each other.
All right, so they're in parallel. What does that mean?
It
Same
means they have the same voltage.
and then same resistance.
Hmm.
And therefore the same power. All right. Now, how should we rank these? All right. So some people like to do voltage first. I always prefer to do current because it's always been more intuitive to me, the current. I always figure out the voltage after I do the current. But which path is going to get more current? So I'm going to draw how many different paths do we have?
4.
3.
3.
Three.
So would you prefer to take a path where you're going to hit 2 stoplights on a 1-lane road, or a path where you're going to hit 2 stoplights, but it goes into 2 lanes? Would you rather drive on a 1-lane highway or 2 lanes?
1 lane.
1 lane.
I can tell you guys didn't grow up in the Midwest. 2 lanes. 2 lanes are so much better. Because let's say there's some idiot driving slow in 1 lane. If you're in a 1-lane highway, you're like, well, I guess we're just here now. If you have 2 lanes, you can pass them. So obviously electrons aren't actually passing each other. But remember, these are in parallel. If we're in parallel, what happens to our resistance?
Decreases.
Decreases. So this path has less resistance than this path. I'm just going to call this path A and B just so I can do things. So the current in A is going to be less than the current in B because you're going to have more electrons wanting to go this way because there is an easier path. They're still going to hit 2 resistors, but they have more options now. There's more space for them to move. More of them are going to go that way. So I know the current through this side is overall bigger than the current through that side. All right. What else do we know? Are 1 and 2 going to split the voltage equally?
Do we know that? Or
We do. Because they're the same resistor. If they weren't the same resistor, we might be able to guess. Hopefully you guys are getting okay at guessing, but if they're the same resistance, we know. We just know it's the same. What about 3, 4, 5? Because that's kind of an interesting situation.
Would 3 have a bigger current?
Okay. If it has a bigger current,
And then it
has more power.
less resistance.
and it has more
Power.
Brightness.
more power. So which one's going to be the brightest one?
3.
3.
3. What do we think between 4, 5, and 1 and 2? Okay. So I'm going to do a little math for this. So basically, we have to figure out some things. How much more current is this side getting from that? Because that'll let us know. If it's getting twice as much and then I split up my current, it's fine because I was getting twice as much current from the get-go. But what do you think? Is this side going to be getting twice as much current?
What was the question?
Is path B, because we already said path B is going to have more current. Is it going to
Yes.
be twice as much current though? And we can do a little bit of math to figure that out. So I'm going to do the resistance for each side. So
Wait, is it because path B has a parallel circuit inside of it?
yes. Alright, so the resistance for path A is just going to be 2R because there's 2 resistors, 2 light bulbs. Path B resistance, we're going to have to do a parallel first. Basically, this, remember, it just means I'm flipping it back over again. So I get 2 over R, and then I'm going to flip it, R over 2 plus R gets us 3 halves R. So basically this is 1/2 R, which is less than 2R. Is it half as much though?
No.
No.
No. So this is going to get more current, but remember, my current splits right here. So while this is getting less current, 1 and 2 is still going to get more current than 3 and 4 are. And if they're getting more current, who's going to have more power?
1 and 2.
1 and 2.
1 and 2. And so again, if there was so little resistance that I doubled my resistance over here, like say if I added more resistors in, then 4 and 5 might be getting so much more current that it makes up for the fact that it splits. But since it's not that much less resistance, it is a little bit, which is why 3 is brighter, but it's not that much less, it doesn't make up for the fact that there's a split. And so whenever I'm not sure, I'll do like a resistance check just to check my math in case. Joseph, do you still need more information on Y3? Okay. So does someone else want to try going over it to summarize? Again, want may be a strong word. Someone want to try it?
Is it because I don't really understand this whole thing, but like I keep on like looking at all the examples. So what I'm seeing is that since 1 and 2 are in the series, they're basically like, I think about it as like the same magnitude in a way.
Mm-hmm.
But then when you look at 3, 4, and 5, 3 is basically sharing the other like part of it with 4 and 5, and 4 and 5 would be less than 1 and 2. I don't know if that makes sense, but like that's what I've been understanding.
Yeah, pretty much. That definitely, it's how it works. And so the reason it works that way is because they're all the same light bulb. As soon as you change the resistors like we do for the labs, it doesn't always work exactly the same, which is why the statistics like we do for the labs are much simpler. But 1 and 2, same resistance. All of them, in fact, have the same resistance. So I'm not really worried about their resistance. What I care about is their current and their voltage. So since they're in series, they get the same current as each other. However, since these are in parallel, they are going to get different current. Since we proved that the resistance is less down path B, this path, than path A, this path, since the resistance is less, more electrons are going to want to go down this path. And since more electrons go down that path, my current increases. If my current increases, my power increases. Because there's a lot of definitions for power, but you can use whichever one you like. They are all the same thing, they're just different algebraic manipulations. So 1 and 2 are the same because the current's the same, resistance the same. 3 is the most because it gets the most current for the same resistance. If I have the same resistance as everyone else, but I have the most current, I will also have the most power. Because if I have the same resistance, most current, I will also have the most voltage. So this one, by virtue of this path being easier, because of this parallel, more electrons will go through number 3. As more electrons go through number 3, it takes up more power. 1 and 2 are greater than 4 and 5 because, yeah, they split the voltage, but they're getting way more current than 4 and 5 are. And so since they're getting way more current, they're also going to be getting a little bit more voltage, even though they're splitting it, and they're going to have more power because of that as well. So yeah, so if you're an electron, not pick 1 and 2, which may seem a little counterintuitive. Sometimes what I like to think is the more paths I can draw through it, probably the easier it is to go. So since I only drew 1 loop through number 1, but I drew 2 loops through number 3 is probably going to be getting more current because that's an easier loop to go through because I could draw more paths, right? The more paths there are to get to a certain place, the easier it is to get to them. So like when you go to school in the morning, there's only really 2 paths you can go to get there. You have, like if you're driving, you're either going into the H lot or the solar lot. And that's why it gets so crazy in the morning. If there were more drop-off points, there'd be less traffic because there'd be more paths to get to the same place. So the more paths there are, the less traffic, the more current, the more flow you get. Since there's only 1 path down this line, there's less flow. So we've already been on air for almost 2 hours. Wait, almost 2 hours now? How are you guys doing?
Mr. Coy?
Yeah.
I have one more question.
Yeah, absolutely.
So, in the equation P equals I squared R, the I and the R aren't inversely proportional, right? Like P isn't constant, right?
Okay, that's probably more complicated of a question than you meant to ask. Kind of. So no, power would not necessarily be considered a constant.
Okay.
These are more like derived equations. So they're not necessarily like a law per se. Well, I think it is actually someone's law, but if you kept power constant, which is actually rather difficult if you're changing things, then they wouldn't be, it would be a little bit, it wouldn't be inversely proportional because of the squared, but they would act in opposite directions.
Mm-hmm.
That's only if you keep power constant, and normally power is not the constant.
Okay.
Could be, but normally not. But yeah, basically we just get these from plugging these in different ways. And basically it keeps the same relationship a little bit too.
Okay.
Does that help your question a bit?
Yeah.
All right, cool. Any other questions? Because basically that's all I wanted to go over for today. I don't want to do the other ones because they get into capacitance, and we really just don't. Like, even in AP Physics 1, you just don't have to do capacitance. There's pretty much, it used to be on the old test, but it's not on the newer one. Probably on Wednesday, I'll probably be doing either page 21 24. I actually really love page 23. It's probably my favorite one to do. Like I still enjoy doing the ones on page 24 because they're complicated and I don't have them memorized yet. And then some ranking problems. So that's pretty much all I want to teach for today. If anyone wants me to do another example or ask some questions, feel free. While you're thinking of things to ask, I'm just going to again quickly go over what we went over in the beginning, aka like what's the week looking like for some of my latecomers. So if you are good, feel free. Have a good rest of your day. But so we had a daily quiz.
Wait, when is spring break?
Next week?
Do we still get videos, or is that like
Do
part
they
of
still,
spring break?
still want videos?
Yeah, sure.
So probably then if you guys still really want them, I will do them. I will be taking like a back seat just so I can like I'm gonna be honest, I'm probably still gonna be working a little bit anyway. But they may just be a little less scheduled. Not that I can really go anywhere or do anything, so probably will still be same place, same time. No assignments, please. Incorrect. Regardless of if this is real class or not, I was already planning on giving you homework over spring break, and I will still be giving you that homework. The good news is, like any homework I give over break, it's very easy to get 100% on. You haven't had a break in a while. I feel like this has been easier in a sense. Like I'm trying not to give as much work, or I'm extremely lenient on it. I don't know if you guys noticed, pretty much anyone who's been turning stuff in has mostly been getting full credit. I am grading it because I want to give you feedback, but I'm not, I don't want you to feel like you're getting punished for not learning something as well because you weren't in school. I do want you to get the practice. I do want you to get feedback, but we are still going to do work. I'm still deciding if I want to do the same thing I did last year or not, which was the same thing as I did over break, which was I gave you FRQ problems and then I gave you the answers and I was like, try it, grade yourself. Probably I'm going to do something similar against to that, but I need to go back and alter them because I had some circuit questions on there and I'm not going to have those anymore. But as far as this week goes, homework 12 is due today. I'm going to post problem set 12 today. As far as homework 13, it's going to just start being review videos. There's really nothing more for you guys to learn. There's technically a little bit more to circuits, but we've already done the basics. It actually would mostly just be practice after this. Circuits labs today or tomorrow, whatever, I don't really care. Just get it in. 7 is due. But there are 8 labs you may have noticed. 8 and 9 are extra credits. So you do not have to do them. They are slightly more complex, but you are welcome to do them and turn them in for extra credit. I'll open up a spot for them in the lab section on the classroom. I'm going to be posting either today or tomorrow frequently tested difficult topics, and that has practice problems as well as the answers and some explanations to the practice problems. And of course, you're welcome to ask questions on things that didn't make sense, preferably on Friday, because I think Friday is going to be more like a true office hours where you come to me with problems and I will answer them. We're getting together a Kahoot for the flashcards, so make sure you're still doing the flashcards. The flashcards are on YouTube, me going over each one. Some are quicker than others. Today we did light bulbs, mostly page 8, numbers 1 through 4. And then this week, probably not till later in the week, definitely not today, I'm going to be posting a resistivity lab. So resistivity, the word resistivity is what it sounds like. It's related to resistance. Resistivity is an innate property of the material. So all of copper has the same resistivity. All of a specific type of wood has the same resistivity. And then you're going to look at what determines their total resistance based on that. So resist, and this is going to be on Pivot Interactive. The resistivity is just how resistive a material is to an electron being pushed through it. So copper, it has extremely low resistivity. That's why we use it as wire. Whereas plastic has an extremely high resistivity. That's why we use it as an insulator to protect us from electric currents. And then Wednesday, I'm going to be releasing a practice test. It's going to open and close Wednesday, so use that window. Tell all your friends. Make sure they did you do it? Check with them Wednesday night. Have you taken the practice test yet? So it's going to be multiple choice and FRQ. So make sure you do take that sometime on Wednesday. I don't know if it's going to release your scores right away. I'm still figuring out the settings on the College Board Classroom. If it doesn't release them Thursday, let me know, because something is wrong, because that's when I wanted them to be released. So make sure you're taking it Wednesday. I think it's going to be the Secure 2017 test. And then some way or another, we are going to do test corrections. I'm not really sure how it's going to work yet, but we'll figure it out. All right, any questions before we call it a day for today? All right, so I'm going to stop the recording.